So in the previous video, I solved this problem in which we were required to find the sum up to the first n natural numbers. And I used this formula for calculating the summation of an AP, but I did not go into the proof behind this formula. So today I'll be trying to give a proof for the same. So I'm gonna be starting with it. So, so I'll be going with the proofs regarding the same. So first, let me define what an AP is. AP, which is also stands for arithmetic progression. So consider a sequence whose first term is A0, second term is A1, third term is A2, fourth term is A3, and so on up to n. So the nth term will be A of n minus 1. So yeah. Now, what an AP is that the so now what an AP is that each adjacent element. So now what an AP is that the next term to a given term differs by a given amount that is fixed for all the terms. What I mean is that the difference between A1 minus A0, I mean the difference between A1 and A0 will be equal to the difference between A2 and A1. But also be equal to the difference between A3 and A2, and so on will be equal to A of n minus 1 and A of n minus 2. And we denote this difference by the term D, which stands for the common difference of this AP. So now what we can say is that if a series is following this condition, then it was called an arithmetic progression. So let me give a few examples of those. So let's consider this series 1, 2, 3, 4, 5, and so on up to let's say 10 or something, maybe infinite. So in this series, we can see that 2 minus 1, which is 1, is also equal to 3 minus 2, is also equal to 4 minus 3, is also equal to 10 minus 9. So we can say that the common difference D for this series is 1. Okay, let us consider another example for this. Let us say the series is something like 1, 10, 19, 28, and so on. In this, we can see that 10 minus 1, which is equal to 9, is also equal to 19 minus 10, is also equal to 28 minus 19. So in this case, the common difference is 9. So you get an idea about what an arithmetic progression is. Now, in the previous video, the question asked us the summation of the first n terms of an arithmetic progression itself. Though the question has more precise values for A0 and D, but we'll consider that later. But first, let's solve it for the general case. So the summation up to the nth term of an AP, that is denoted by S of n, but since the nth term is by n minus 1, I will consider this as S of n minus 1, that is summation up to the n minus 1th term, or I can say the summation up to this term, not the n minus 1, but summation up to this term. Or if it is confusing, I will just change it a bit. So let us change this sequence from A0 to A1. Let us say the sequence starts from A1 and the second term is A2, A3, A4, and so on up to AN, because it's a bit more legible to understand and easier to grasp. So now the summation of the first n terms is equal to A1 plus A2 plus so on up to AN, which can be written as a summation running from I equal to 1 up to I equal to n, and the term that we are adding every time is A of I. This is the mathematical representation of this expression itself. So yeah, now we are required to find the value of this Sn in terms of n. So what do I mean by that is that I need to generate a formula for Sn so that I do not need to compute the entire series, but instead I can find the summation by just using the value of n itself. So Let me just give it a heading here. Derivation for the formula to compute the summation of first n terms of an AP. So as we saw that the first n terms were given by A1 plus A2 plus A3 plus dot 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 plus A of n minus 1 plus A of n. So this is what we want to compute. Now, if you try to use this property of an arithmetic progression, that is the difference between the two consecutive terms is d. So what I can do is I can say that A2 minus A1 is equal to d. So if I try to transform this equation a bit, so I can say that A2 is equal to A1 plus d. Similarly, if you try to do it for any ith term, we can say that A of I is equal to A of I minus 1 plus d. Okay, so we got this. So now what I can say is if A2 is equal to A1 plus d, then A3 is equal to A2 plus d. But A2 has also been expressed in terms of A1. So we can further replace this with A1 plus d and again a plus d of that. So it can be written as A1 plus 2d. Similarly, I'm going to replace all the terms in this series in the form of A1 and d. And I'm sorry for a mistake when I said about the formula for Sn. The formula for Sn would be something that will just require the first term of the series and the number of terms and the common difference. I will repeat. We are trying to generate a formula for computing the sums, for computing the sum up to the nth term of an AP with only the number of terms that are there, the first term of the series, and the common difference of the series. So these are three parameters that we are expecting. So first, let me just replace these values with what I just said. So A1, and this can be written as A1 plus D. This can be written as A1 plus 2D. And again, if I try to write A3 in this, sorry, I mean A4, it can be written as A3 plus D, which is A1 plus 2D plus D, which is A1 plus 3D. So I can write this as A1 plus 3D. And similarly, for the n minus 1th term, it can be written as A1 plus, if I see that if the first term had no D, the second term had 1D, so it is having like exactly I minus 1 Ds. So the n minus 1th term will have n minus 1 minus 1 Ds, plus the nth term will have 1 plus n minus 1 Ds. So this is after writing this expression in terms of A1 and D. Now, what I'm going to do is a little neat trick, that is, I'm going to reverse this series, that is this expression actually, not this series, this expression. Since addition is commutative, I can do this without having any effect on the results. So then new series will be like A1 plus n minus 1 into D plus A1 plus n minus 1 minus 1 into D plus up to A1 plus 2D plus A1 plus D. Actually, I'm going to make something like this because I want the number of terms at the beginning and ending to be the same. I'm going to remove these two terms. You can keep them as well, but that will just lengthen the proof more than we are required to do. So now what I'm going to do is, if I call this expression as 1 and this expression as 2, so now what I'm going to do is add these two expressions, 1 plus 2. So the LHS will become twice of Sn, and over here we will get A1 plus A1 plus n minus 1 into D. If I add this term and this term together, I mean this term and this term together. After adding that, I get this. Similarly, if I do for the second term, I will get a1 plus d plus a1 plus n minus 1 minus 1 into d. I can just write this as n minus 2, and so on. If I continue, I will get a1 plus n minus 2 into d plus a1 plus d. Similarly, the last term will be a1 plus n minus 1 into d plus a1 plus d. So that is what I will get, and if I try to just simplify the equation a bit, I will get as twice of a1 plus n minus 1 into d plus similarly over here I will get twice of a1 plus, if you try to say n minus 2d plus d, which will be n minus 1d, n minus 1d plus dot 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 up to the second last term will be twice of a1 plus, if you try to add it again, it will again be n minus 1d, and similarly for the last term it will again be twice of this plus n minus 1 into d. So what I can see that each of these terms are identical. That is, we are having n copies which are exactly the same. So what I can write it as is twice of Sn will be n times this term itself. That is 2 times of a1 plus n minus 1 times d. And since on the LHS I have 2Sn, in order to compute S of n, I will divide both the sides by 2, and I will get n over 2 times twice of the first term of the series plus the number of terms minus 1 times the common difference in the series. So this is how we can compute the sum of an AP in terms of the first term, the number of terms, and the common difference of the series only. So this is the proof behind the formula that we used in the previous video. So if you have any doubts regarding this, leave them in the comment section. I will make sure to answer them. And if you like this video, make sure to hit that like button and subscribe if you are new to the channel. So thank you and see you in the next video.